me that there was some question about the Momer-Sorensen gate in the tutorial, but I didn't quite understand what the question was. So does someone want to ask it?
I just think that the main confusion was that the diagram was a little bit unclear what it meant. So we spent most of the time trying to understand the diagram, basically. I don't know.
Okay. So here's the diagram. I mean, do I need to explain it now, or do you guys figure it out then?
I think we have like a rough idea, but it would be at least easily useful. Mm-hmm. I don't know.
Sure. Okay. So so here we have GG and N. So this is the two atoms, ground, ground, and the phonon, N. So this is EG, and this is going to be N minus 1 and N plus 1 in the phonon. And then something similar over here for GE. And then up here we have EEN. And so we have there. Ooh. So there's two lasers. The red one is kind of roughly the energy difference between G and E minus the energy of one phonon, but it's not quite that. So it's going here, but it's a little bit off. It's a little bit low. And so that's this transition. But it could also do this transition, right? That's the same energy difference there. And then the blue one is the opposite. It's the energy difference between G and E plus one phonon. But again, it's slightly off. Here, let's get a little more precise here. So this one is here, but you could also do this transition. The same thing on the other side. And I don't know, that's the diagram, right? So the point is that because these are not exactly on, there's a delta detuning, and so you don't populate this transition. That was one of the questions.
Yeah. I think one of the questions was in the ground state and in the excited states, we also have EEN plus 1 that we should be able to access.
Sure. So, okay, go ahead.
No, I think just trying to.
Yeah. So I mean, so I have to say that. I mean, I was looking at the paper and trying to figure out what the question was. I guess I'm also a little confused as to why you don't get transitions between GG and EEN plus 2 with two blue phonons. Two blue photons either way. I expect there's some cancellation that happens there. I haven't calculated it, and it doesn't really say in the paper that I could see. But probably that's what happens because two blues. It's the same thing left and right, and if there's a sign difference because of something, then there's some business about canceling stuff out, the level shifts and stuff like that, and so that may also cause it to cancel.
Okay. Oh.
Okay. So are there other questions about stuff that we've been doing so far? Okay, so this week we're going to do a different topic, much more computer science-y. And so we're going to study complexity in algorithms. So today I want to get started by talking about complexity and kind of what it means when we talk about computational problems and what we mean by the amount of time it takes to solve a problem. So, so the basic idea is in complexity theories, we'd like to classify some computational problems as hard and some computational problems as easy. And so let's go through let's think about for a bit about what that should mean. Okay? So one thing you could take it to mean would be, well, let's set some time t. This is the amount of time we're willing to spend on a problem. And if the problem takes more than that, it's hard. And if it takes less than that, it's easier. Right? So that, at first blush, seems like a reasonable definition. It's certainly a practical definition. But the problem with that is that, obviously, if you get a new computer and it's faster, then it's going to solve the problem faster, right? And so if it took t plus a little bit, then maybe it used to be hard and now it's easy. So that doesn't seem right? Because this is not a property of the problem, whether it's hard or easy. It's a property of your computer. And some computers might be faster at some things than others, a little bit optimized for one thing versus the other. And so then it's really dependent on what computer you have, right? Some problems that were easy on one computer might be hard on another, while other problems that were hard are easy instead. So, so that's not a good strategy. We really want a property of the problem to say whether it's a hard problem or an easy problem. And so let's do something that's a bit more machine independent. So we might talk about, say, the number of computational steps it takes to solve a problem. So that's a bit better. But you see, it still depends on some details of the machine, right? We talked about different universal gate sets. And you can easily imagine that a certain problem might take some number of steps n on one machine, but it might take 2n on a machine using a different set of universal gates, because you have to build up the gates that you need for this problem, this algorithm, out of smaller pieces. So that's one issue with there. And the other thing is you might say, well, here's actually a very simple algorithm. We have some problem. It has an answer. So let's write a program that outputs that answer, right? The answer is y, so the program will just say y. And that's it. It's a very short program. And it will give you the answer to this particular question. Okay? So if we want to say what's the best program to answer this question, well, there it is. That's very short. Okay? Now, obviously, this is cheating, because in order to write this program, we have to already know what the answer is. But, we certainly say it's acceptable to study this problem a lot and figure out lots of stuff about it to come up with a good algorithm for it. So what's the difference between these? Right? And as long as you're talking about just a single question that has just a single answer, there actually is no difference. Right? If you study the problem enough, you'll figure out the answer, and then you can write a very short program that outputs that answer. Okay, so in order for this to make sense, to talk about the complexity of problems, we have to talk not just about the complexity of answering a single question, but the complexity of answering a set of questions. Okay, and we're going to look at some big set of questions and say, what's an algorithm that can answer any question from this set? And then we want to try to find the shortest algorithm that can do that. So in order to set up the framework here, let me just define some notation. So we have the set 0, 1 star is the set of all bit strings of any length. Finite bit strings. So we're talking zeros in that set. Nothing, the empty string is in that set. 0, 1, 1, 1, 0, 0, 0, 0, 1 is in that set, and so on. And so the size of is the length of the string which is, any non-negative integer. And then we say a language is a subset. And so this is a bit mysterious definition if you first come across it. So what do I really mean when I want to talk about a subset of 0, 1 star? So I'm talking about some subset of bit strings. And what does that mean by saying it's a language? And how does that correspond to a problem in particular? So the interpretation here so we have bit strings as input to our problem. Arbitrary bit strings. And the ones in the language are inputs where the answer is yes. The others give the answer no. OK, so here's a concrete example. So this is, in computer science lingo, known as primes. Given x is x prime. OK, so now we're going to interpret the bit string as the binary representation of some integer, non-negative integer. But I guess we could probably take x to be, in that interpretation, at least 2 in order for it to be totally well defined. And then the yes, and we're going to get the yes answer when it's prime, and no answer if it's not prime. So for instance, 1, 0 represents 2, so that's in the language. 1, 1 is 3, that's in the language. 1, 0, 0, that's 4, it's not in the language. OK? So does this make sense? OK. So here's another definition. So we say an algorithm A of x decides a language if for all x in 0, 1 star, A of x equals 0 if x is in the language, sorry, if x is not in the language, and A of x equals 1 if x is in the language. OK? So I didn't really define an algorithm, but an algorithm is, we can think of it as some sequence of gates. Given the input x, we run this sequence of gates, which could depend on the size of x. So this is why I'm not defining algorithm. It's actually a little bit subtle. But it's some sequence, and ultimately it's a function. And it outputs some value which depends on the input x, right? And so we say it decides the language if it can tell us if x is in the language or not. OK, so some more terminology here. So x is an instance of the language, and it's a yes instance. If it's in the language, and a no instance if it's not in language. Okay, so obviously in this case, since the inputs are arbitrary bit strings, we can interpret any bit string as an instance of the language. But it's partly a question of interpretation. And sometimes we're going to be talking about promise problems. And in that case, the possible inputs are some subset, some proper subset of all bit strings. So we'll only take bit strings that have certain properties. And then the instances will just be the allowed inputs to the problem. OK? So are there questions on these definitions so far? OK, so let's go back to this example of primality testing. So here's a very simple algorithm that decides this problem. So let's step through y from 1 to x and try dividing x by y. If that works, if we get an integer, then we output no or 0. Otherwise, continue. Right? So clearly, this algorithm decides the primes problem, right? Because if x has some factor, some non-trivial factor, it will find it. And I guess I should say at the end, if it gets to the end and it at end output yes. If it doesn't have a factor, then it'll get to the end without finding a factor, and so it'll output yes, the number is prime, right? And so clearly, this will work correctly. Yes? Do I need to explain that? I hope not. OK, so then the next question is how long this takes, right? And that's kind of where the realm of complexity starts, is counting how long algorithms take. So how long does this take? Well, so every time we do one of these divisions, it takes about log x squared steps. And of course, this is just using kind of standard long division. You can speed it up. There's some tricks, but that's not too important right now. And how many divisions do we have to do? Well, it depends on what the number is, right? So if so this is an upper bound, because this is for the cases where y has a similar number of digits to x. Right? Obviously, if y is very small, then this is faster. But for most y, this is how long it's going to take. Now, obviously, if x is, say, even, then this algorithm will very quickly find that it's even, right? Because the first thing we'll try will be 2. We'll divide by 2, and it works. But if x has only very big factors, or if x is prime, we're going to have to try everything. And so we might have to do up to, well, I guess it's x minus 2 divisions. And this is kind of roughly log squared. I guess there's some other factors in there. And so the time to do this whole thing is roughly, let's ignore the minus 2. So it's x log x squared. OK? And what we like to do usually is talk about complexity as a function of the size of the input. OK? And so in this case, the size of the input is log x. So this algorithm takes a time that's exponential in the size. OK? So that's a long time, right? If x is a really big number, hundreds of digits long, then that's a really, really, really long time. OK? And so you don't want to have to use this algorithm. And it turns out that there are, in fact, much, much better algorithms for testing primality. So that underlines another point, that when we talk about the complexity of a problem, we shouldn't just say, how long does this algorithm take? That's the first one we thought of. We should say, how long is the best algorithm take? And another point is that it's not enough to say, well, sometimes this algorithm is very fast, because sometimes it's also very slow. And so normally, this is not an absolute rule, but normally in complexity, we talk about the worst case complexity. We say, for the worst possible input, how long does this algorithm take? OK. Right. So now again, remember. So why was I comfortable not saying exactly how many steps this was? Partly because I'm just giving you the general idea, but there's a more fundamental reason for that. Remember, which is that if you look at different universal gate sets, it might be the exact number of steps is different, right? Maybe I have a dedicated arithmetic chip, and it can do 2-digit divisions, just kind of like as one step. There's some table that you look it up, and it gives you the answer. But maybe you have to build it out of more fundamental gates, and it takes 10 times as many steps, something like that. So the exact constant factor in front of here is again going to be kind of machine dependent. It's going to depend on our exact universal set of gates. And if you think about it, it depends on more than that, right? So let's think about last week we were talking about the difference between, say, computers like ion traps, where you have long-range gates very easily if they're networked by light, versus something like superconductors, where we only really want to do gates between qubits that are sitting next to each other. So what does that mean? Well, if we have an algorithm that calls for us to do a gate that interacts 2 bits that are very far apart in our computer, let's say distance n apart, well, in the case where we can do long-range gates, that's just one step. In the case where they're nearest neighbor gates, we have to, say, move these bits so that they're next to each other, and then interact them, and then possibly move them back. And so that's an extra factor of n in there, right? And so that means that, and if the input is size x, we're going to have at least x bits, size, absolute value of x, size of x, bits in our computer, probably many more, and bits could very reasonably be that far apart. Okay, so the difference between a computer that lets us do long-range gates and one that lets us do nearest neighbor gates could be a factor, certainly a factor of the size of the input, right? And so the difference even between, say, log x squared, that would make this like log x cubed instead, if we had to do that. And there's other variations of computational models you can think of, Turing machines, and you can say, well, actually, how far apart do they have to be? In 1 dimension, in 2 dimensions, in 3 dimensions, those answers would be different. right? So there's lots of possibilities there. And so the upshot is that we only usually talk about computational complexity up to polynomial factors, because polynomial factors can differ between different computers. So let's see. So in complexity theoretic language, certainly the constants don't matter. And like I said, even the polynomials can differ. So we frequently talk about complexity using something called big O notation. And there's a good chance you've used this informally, even in physics. But in computer science, it has a very precise meaning, which is this. So we say a function f of n is O of g of n, for g of n some other function, if there exist constants n0 and c such that f of n is less than or equal to c g of n for all n greater than n0. Okay? So this is saying that for sufficiently large n, f and g differ by a constant. Of course, big O notation is kind of just one way. It's just saying actually that f is less than or equal to this. So it could be smaller than that. But there's other variants. There's little o notation, which means that it actually is strictly smaller, and big omega notation, which says that it's strictly bigger. And then big theta says it's the same. I don't know that I'll be using these other ones. But this is certainly the most common thing that you'll see. Okay? So the upshot is that using this big O notation, I could say that this particular factoring algorithm is O of x log x squared. That's really what I meant when I had that tilde there. Okay. But this still is just capturing up to polynomials. You could say something is O of n squared, or O of n to the 4th, or O of n to the 20th. But all of those differ by polynomials. And so we like to define a complexity class that's kind of robust against those changes. So we say a complexity class is a set of languages remember, language is basically a problem, a computational problem. And so then here's an example of a complexity class, probably the most important one. So the set P is the set of languages that can be decided in time O of x to the n for some n. Okay? So this is the set of languages for which there exists an algorithm that runs in polynomial time. And that polynomial could be anything. Okay? And again, the reason I'm doing this is because on different machines, that polynomial might be different, right? If we express our algorithm in different ways in terms of nearest neighbor gates versus long-range gates, and on a Turing machine, whatever, the exact polynomial might be different, but it'll still be polynomial. And I'll get back to that in a minute. Okay? And so in particular, this is going to be usually our criterion, at least for classical computers, of what problems are hard and what problems are easy. So if a language is in P, we say that there is an efficient algorithm. Or that L is easy. And if not, it's hard. OK? So it's not at all obvious. So based on our discussion up here, you might think that primes is an example that's hard, right? Because this algorithm that we came up with takes exponential time in terms of the input size. And the input size is appearing here, remember. So this is kind of very explicitly saying that we want polynomial in terms of the size of the input. But it turns out there's algorithms, like I said, that are much better than this. Certainly, you can immediately make lots of improvements, right? You can say, well, I don't really need to go all the way up to x. I only need to go up to square root of x. And I don't need to divide by every number. I only need to divide by prime numbers. But both of those will still leave it exponential in the input size. But it turns out there's an algorithm, and it's a very non-trivial algorithm. I mean, it's non-trivial in the sense that it wasn't discovered until 2002. So classical computer science had been around for a long time. That solves this primes problem in a time that's polynomial in the size of the input. OK? And so this underscores that it really is important to look at the best algorithm that exists, right? And that means it's very hard to determine if a problem really is in P or not, right? If you can find an efficient algorithm, then yes, you know it's in P. But if you can't find one, maybe you just didn't try hard enough. OK? But the flip side of this is that while primes is in P, we know there's definitely problems that are not in P, that are outside this class. OK? And that's a somewhat profound statement already. I mean, if you watch movies about computers, you would never believe this, because if there's some computational problem, the heroes will always be able to sit down and for 10 minutes, or maybe it's an hour if they really want to make the time seem exciting, and write a program that will solve this problem. But in real life, that's not true. There's some problems that are simply too hard to be solved efficiently. OK? And actually, what Turing discovered is something that's even stronger than that. There are some problems where there's no algorithm at all that decides the language. Not just no efficient algorithm, no algorithm at all. OK? So the standard example of that in Turing's original proof is the halting problem. So the halting problem says, OK, here's a computer program. Does it run forever, or does it stop after some finite amount of time on some standard input, say? OK? So you can see that this is actually kind of a practical problem, right? If you're writing a program, there might be some bugs in it. You want to look at it and see if it actually will terminate at some reasonable time, or if it'll go on forever. But it turns out, and the proof is beautiful but a little beyond the scope of this class, that there is no algorithm that will solve the halting problem for arbitrary input. I mean, here's an easy way you could try to solve it. You could say, oh, I have this program. I'll just try running it. And if it stops, then I know it does halt. But you see the problem with that, which is that if it doesn't stop, you don't know if it's going to stop in a few more steps, and you could keep on trying, or if it's going to be a million more steps, or 10 to the 10 to the 10 to the 10 to the 100 more steps, or never, right? And so you would have to somehow get into the guts of this program and see, oh, there's an infinite loop there, but maybe it depends on some more complicated thing. And it turns out there actually is no way to solve this problem. OK, so but then once you're faced with this issue of undecidability and uncomputability, I actually should say they're uncomputable. Undecidable is Gödel's. And they are closely related, Gödel's theorem and uncomputability. Once you're faced with this problem, you might have a crisis of worrying that our whole goal in complexity theory is misguided, right? What if you have one computer where there's certain problems, like the halting problem, that are uncomputable, but you have a different design of a computer, maybe a very different design, where there's a totally different set of problems that are uncomputable. So we could then, problems that are uncomputable on the first computer might be solvable on the second computer, but not, and vice versa, right? Then which one is the kind of the right notion of complexity? However, we believe that that's not the case. And this is encoded. Okay, let me start a new board. In the Church-Turing thesis. And the Church-Turing thesis says that all physically reasonable models of computation have the same set of computable functions. OK, so what does that mean? That means that if you have the Windows machine and the Mac machine, they can compute the same functions. And of course, so far I've just been talking about classical computers, but of course the point of this class is to talk about quantum computers. So you might ask, well, what about quantum computers? Maybe they can compute some functions that are classically uncomputable. But if you think about it a little bit, you'll see the answer to that is no, definitely not. And why is that? Because we're not making any constraint on how long it takes, right? We just want to say, can they be computed? And if you have a quantum computer, well, a circuit, a quantum circuit, is a sequence of unitaries. So we can write each of those unitaries down as a big matrix. If there's n qubits, it's a 2 to the n by 2 to the n matrix. And we can multiply those matrices together, right? Sure, that takes a long time. But remember, just if we're just talking about computability, we don't care how long it takes. And so any quantum computation, you can definitely calculate the answer on a classical computer. It just might take a really long time. OK? And so that, of course, is the next question. If we really want to talk about complexity theory, we want to divide things into easy and hard problems. Does the class of easy and hard problems depend on what kind of computer we want? Does it depend if we have Windows or Mac? And so that's handled by a strengthening of this, which is the strong Church-Turing thesis. Which says the same thing, but with efficient algorithms. Okay, and this is saying that if you have two different classical computers, or really the original version of strong Turing thesis is two different types of computers, and you want to calculate how many steps on one computer versus the other computer, the difference is only going to be some polynomial. Yeah?
What is physically reasonable?
Yeah, so that's an excellent question. And I said, I was going to be talking about a very computer science-y thing this week, but here I somehow stuck in a physics word. And so the thing is that you can come up, and people have over the years come up with all sorts of models of computation that seem to violate these two statements, right? So here's an example. Here's a very concrete example. So if you have an analog machine, so instead of having bits in it, 0 and 1, it has registers that could be some real number. Okay, could be between 0 and 1. Say it's you have something here, and the value is just you have a ball, and exactly where that ball is your register. Okay, and it turns out that if you do computation with machines that have real values in them to infinite precision, then you can actually solve things like the halting problem. Okay? But if you think about this, that's not really physically reasonable, that the position of something has an infinite precision value in your computer's register, right? Any kind of error at all will mess that up, right? And you'll have only finitely many bits of precision, right? If it's really, really accurate, that might be 10 or 100 bits of precision, but that's still only finite. And in order to actually make the halting problem work, you need really infinite precision. Okay, so that's an example of a physically unrealistic or unreasonable model of computation that does, in fact, differ from this Church-Turing thesis. So another example that's unreasonable is if you allow kind of infinite amounts of energy, you can do things arbitrarily fast, right? And okay, that's not really affecting the number of steps, but in some sense, if it's letting you do things arbitrarily fast, then you can in finite time do an infinite amount of computation, which is also kind of unreasonable. Okay, and so when quantum computers first appeared, a lot of classical computer scientists thought, and I think some still think, that, oh, this is just another physically unreasonable model of computation. Because quantum computers, it appears, violate this strong Church-Turing thesis. Okay? And we'll see examples of that over the course of the week. Now, there's a caveat here, which is I said it's very hard to prove a problem's actually not in P. Right? Because you can't just say, well, I tried to find an algorithm and I couldn't. That's not good enough. It could be that there's an algorithm that we haven't found. And so it remains a logical possibility that there is an efficient classical algorithm for simulating quantum computers, and that actually all the quantum complexity, well, the quantum algorithms can also be, efficient quantum algorithms can also be solved in P. That's possible. I don't think it's very likely. I don't know that there's too many people who do think it's likely. But we can't rule that out. Nevertheless, it appears, based on the examples we have, that that quantum computers do, in fact, violate this strong Church-Turing thesis. But there does seem to be some quantum version of this. Which would say that it doesn't really matter what kind of quantum computer you have. No, let me rephrase that. And in particular, you might say that any physically reasonable model of computation can be simulated in polynomial time on a quantum computer. And so what does this mean? This means that, well, certainly if you're building quantum computers out of ion traps or out of superconductors or out of photons, they should all be able to efficiently solve the same quantum algorithms. It also means that if you start to bring in quantum field theory, that there should be an efficient quantum algorithm to solve problems in that. And if it's true, it also means that once you have a theory of quantum gravity, that it should be true that a quantum computer can efficiently simulate that as well. Okay. Of course, it could be that quantum gravity is going beyond quantum mechanics, and this is not true anymore. There could be some new physical principle. So I mean, and that fundamental question is why quantum computers are really a big deal for classical computer science, because it shows that the model of computation is not just some God-given thing. It depends on it depends on the actual physics of the real world, which I guess could also be God-given. But it's, in the mathematical sense of this is the right model of computation versus the physics sense. It means that computer science really does have to look to physics to find out what is a reasonable model of computation. It's not just something you can derive by pure thought. OK? So are there questions on this? Yeah.
What do you mean here by quantum computer? Like, is there?
Yeah. So a quantum computer. Let's just think of it as, so polynomial time means it's going to be a quantum circuit of polynomial size in the input. There's a little bit more details if you really want to define it carefully, but that's basically it. Okay? But of course, part of the point of this quantum curve Turing thesis is it's not very sensitive to the exact definition. So I could define a quantum Turing machine and use that. I could say, well, my quantum circuits, I want them to be restricted to nearest neighbor gates in 1 dimension or 2 dimensions. And that's only polynomial differences here. So this is still true, no matter how you do that. Yeah?
But I don't see the connection with physics that you were saying. Can you please elaborate?
Yeah. So suppose the universe really were classical. OK? Then this strong curve Turing thesis would be correct. And the model of computation we should use should be one of these classical models of computation. We should only use classical reversible gates or a classical Turing machine or something like that. But if quantum computers really are more powerful than classical computers, then we say, well, if the universe is really quantum mechanical, then this is right. But some people think that, well, there's some fundamental source of decoherence. And depending on the nature of that fundamental source of decoherence, it might say, well, if you have a really big entangled quantum state, it will very rapidly collapse to some classical state. And if that's true, then maybe quantum computers are impossible. And we're back there. Okay? And that's a physics question, right? Whether that's true or not. On the other hand, it could be that, quantum gravity allows you to do some sort of nonlinear quantum effect. And that might let us do some things that are more powerful than quantum computation. And again, that's a physics question. Any other questions? OK. So let's go back to the question of showing problems are hard. So one way to do that you might hope to do that, is to try to classify hard problems in a more refined way, rather than just say, oh, well, there's no polynomial time algorithm. That's it. Certainly some problems that are harder than other problems. And so you can try to impose some structure and see what happens. So one complexity class that turns out to be very important is the complexity class called NP. So in P has an obvious meaning. It stands for polynomial. This NP stands for non-deterministic polynomial, which is one of these kind of unrealistic models of computation, but it's useful for defining this class. I'm not going to define that, but you can define it this way. So it's the class of languages such that there exists a verifier algorithm V, and V takes two inputs, x, w. So x is the instance of L that we're concerned about. So three properties should hold. So first of all, V of xw runs in time that's polynomial in x for all x and w such that the size of w is a polynomial in x, size of x. And so this verifier algorithm is supposed to check if x is really in the language or not. Okay, so maybe I should explain the definition a little bit more. So we have some class of languages. We expect they might be hard problems to solve. So we don't necessarily have an algorithm that will decide them, or an efficient algorithm that will decide them. But we have this verifier algorithm, which runs in polynomial time. So it's an efficient algorithm. And what it does is it takes an additional input. And so W is going to be called the witness. And if somebody gives us W, then we can check that x really is in the language. And so W is supposed to exist if x is in the language, and it's not supposed to exist if x is not in the language. So in particular, we say that when x is in the language, there exists this witness wx. Yeah, wx is the witness for x. Exists wx such that v of x wx equals yes. And of course, the size of wx should be reasonable. OK? And if x is not in the language, then for all w, and I guess I put in the condition that w is polynomial size, although I don't think that's really necessary. Then if we try to run this verifier algorithm, it will say, no, that doesn't work. OK? So once again, NP is the class of problems for which there's an algorithm given some extra information that lets us check that something is in the language. OK, and let me give you an example that will hopefully help you understand this definition. So this one is called KSAT for K satisfiability. So instances is a binary encoding of some logical formula. Formula has n variables. Xi. And it consists of the and of some number of clauses, which is not too many, and each CI is the OR of k atoms, each of which is either a variable or the negation. And then we say, so the class Ksat is the set of inputs, of instances, f of x. So it's a yes instance. Of Ksat if there exists so exists some satisfying assignment so xi, each xi goes to true or false, 0, 1. And this satisfying assignment has the property that f, so x here is a vector of the things, evaluates to true. Okay, I guess I'm kind of switching notation here. Let's make this false, true. Okay, so let me give you a concrete example. Here's a very simple one. So we're just going to have two variables, and let's do 2sat. So we're going to have x1 or not x1, and x1 or x2. Okay. So we have, this is our first clause, this is our second clause. And so is this formula in 2sat or not? Is there a satisfying assignment of variables to it?
Will 1, 1 work?
Will 1, 1 work? Well, let's see. So, so if x1 is 1, then is this first clause satisfied or not? Well, this is true, this is false, but true or false is true, so that's OK. And here we have 1, 1, so true or true. That's also true. So both clauses are satisfied, and therefore, yes, that's a satisfying assignment. And actually, there's lots of satisfying assignments in this case, right? All we need is that one. This one is trivial. This clause is always satisfied, right? Whether x1 is true or false. And this one is satisfied if either x1 or x2 is true, or both. But you can also easily come up with things that can't be satisfied. So here's an example. Again, with two variables and two clauses. So we can have x1 or x1 and not x1 or not x1. OK? So in this case, I'm ignoring the second variable. I don't use it at all. It doesn't appear in any of these clauses. But in the first clause, this is satisfied whenever x1 is true, but only then. And the second clause is satisfied whenever x1 is false, but only then. So these two things are contradictory, and there's no satisfying assignment. OK? And so hopefully those two examples help you see that this problem is an NP. Right? Because what's the verifying algorithm? Well, first of all, what's the witness? The witness is, I'll give you some assignment of variables. I'll say x1 is true, x2 is false, x3 is true, and so on. And then the verifying algorithm is you plug it into the formula and try it out to see if it works. OK? But you can see that if somebody doesn't give you the witness, then this could take a very long time to figure out. Because you might say, well, I have to try all possible assignments of variables to see. OK? So this is an example of a problem that's in NP but is not known to be in P. OK, I'm going to stop there. There's a little bit more to this that I'll do tomorrow. But are there questions on what we've done so far? OK.